So let's begin our review of Stoichiometry 1 2009 FRQ adapted. It's adapted because I've changed the problem a little bit to fit our stoichiometry needs right now in class. So the spirit of the question is still there. I just made a small little changes so that we can do the entire problem. Okay, so let's be crazy and start in order with number one. We're going to balance the reaction. And this, of course, is due to the law of conservation of mass. And like Antoine Lavoisier showed us, that the number and types of atoms must be the same on both sides. Now, he didn't quite say that, but essentially, he alluded to the fact that the mass of the reactants must equal the mass of the products, because what we're going to do here is have the same number and same type of atoms on both sides. So very quickly, I can see on the reactant side, there are 2 hydrogen atoms and 2 oxygen atoms. And I can see we have a problem on the reactant side. We have 3 oxygen atoms, 2 from the oxygen and 1 from the water here. So to fix this kind of 3 and 2 scenario, what I'm going to do here, and it's a puzzle, okay, I'm going to put a 2 here. And what that does, party people, it gives me 2 oxygens by distributing that, and I already have 2 on the O2 side, so I have a total of 4 oxygens, 4 O's. And to get 4 oxygens on the reactant side, I would need to put a coefficient of 2. We call these coefficients, and these are the ratios of the entire molecule here. All right, so the numbers in front tell us how many of those molecules, and of course the subscripts are part of the ratio of atoms within that particle. Okay, so it's important we get that. So cleaning this up, we should get that there is going to be a ratio of 2 H2O2s, that's hydrogen peroxide, and there's going to be 1 oxygen. You don't have to put the 1 there, but it's implied. Like if I give you an apple, it's 1 apple. 1 oxygen and 2 water molecules. So it's a 2, 1 to 2 ratio. Okay, and again, to make sure that we know we balance, we can clearly see, hopefully, that we have 2 times 2 is 4 hydrogens. We have 2 times 2, I'm timesing the coefficient by the subscript, that gives me 4 hydrogens. And then, of course, 2 times this 2 here gives me 4 oxygens, and I have the same scenario, 2 oxygens here plus the 2 here. So any case, that's all I did there is balance the reaction and to make sure I have the same type and same number of atoms on both sides. That is absolutely required in order to solve these next problems, because in these next problems, party people, what I'm doing is we're doing ratios of the actual molecules or formulas in a tile reaction. We have been spending most of our time dealing with ratios of how many different atoms are in a chemical formula, whether that be empirical or molecular. Now we're going to deal with these ratios within a chemical reaction. Okay, so very important that you balance before we go forward. So that covers number 1. 2 to 1 to 2 ratio. All right, so on to this little blurb here that's going to help us answer number 2. The mass of an aqueous solution of H2O2 is 6.9.51 grams. That's the mass of my starting reactant here, and I'll put that up there. Okay, and the H2O2, which is the reactant in solution, decomposes completely according to the reaction represented above. The O2 produced is collected in an inverted graduated tube, water, okay, intertube over water at 23.4 degrees Celsius and has a dry volume of 178.2 milliliters. And the density of the O2 gas is 1.48 grams per liter. Let me explain this. We haven't done this lab, but we will. So essentially what we're doing is we're taking some kind of container, let's do this, some kind of container, some kind of flask, my flasks are kind of ugly, and we're filling it with some amount of H2O2 solution. Notice it's aqueous, so it's not pure hydrogen peroxide, it's hydrogen peroxide mixed with water homogeneously, it's a mixture. And what we're going to do is we're going to decompose it. So we're probably going to cap this reaction. And then we're going to take let's say some kind of aquarium tubing we could use, or some kind of flexible tubing. So we have a stopper here with maybe a glass little tube connected here. But bottom line is the products of the O2, in this case the gas that's released when this decomposes, is going to go through this tube. Let's change that color to like a black little circle. And these gases will travel. Okay, these are little bubble gases. Okay, you can't see them, of course, but they're going to travel into this tube, and we're going to collect water by water displacement. This is going to make more sense when we do the lab, but I want to do the math anyway. And now we're going to have this tube inside a container that's filled with water, and I guess I kind of made that container too big. And that container is going to have a tube, and that tube is going to be filled with some sort of, not some sort of, but definitely water. Okay, I can't color within the lines. And so when I invert that, and I don't have an easy way to invert that, so I'll draw that again. So the tube is going to be inverted and pushed underwater, and that tube is going to be under that tube there. And when this gas bubbles, it's going to push all of that water out, and we're going to collect the O2 gas right there. I'm trying to make a nice key. So that's O2 gas. And when the gas collects, and let's draw our little what? Let's draw our bubbles. Uh-oh, bubbles. Okay, I can do this. So when these bubbles go up because they're less dense than water, they get into this space here, and they push the water out. It's called water displacement. So as the gas bubbles up, it collects to the top, and it essentially pushes the water outward. It's called water displacement. If I again produce more oxygen, I'll have a greater volume of O2. So in any case, this amount of gas we can actually read by how much water leaves, and they're saying that the amount of gas collected by this reaction is 178.2 milliliters. Don't forget, milliliters is a space, is a volume. So we decomposed all of the H2O2 that was in the solution, and it became oxygen gas in the form of this volume of gas. All right. So the first question is calculate the number of moles of O2 produced in the reaction. Now some of you guys are pretty smart, and you recognize, oh well, I know that 1 mole of any gas at standard temperature and pressure is 22.4 liters. I'm all set for this reaction. Well, the problem with that is that we're not at standard temperature and pressure. Right away, I've given you a temperature that's not standard, and you don't know the atmospheric pressure. Okay, so without that, we can't do that nice conversion of 22.4 liters equals 1 mole. But we have something else just as important. We have the density. So, and notice the density is in grams per liter. That's what we do a lot for gases. So in order to find the moles of the oxygen, I'm going to take this volume, and I'm going to go 178.2 milliliters. I'm going to convert to liters, and I know I can just move the decimal place, but I'm just going to make this nice and pretty. And I'm going to get rid of milliliters, and I know that 1,000 milliliters equals 1 liter. And I know that my milliliters cancel, and I'm left with liters. Okay, great job, Grodsky. Now, what am I going to do next? Why did I go to liters? Well, I know that my density is really converting factor. I can convert my liters into grams. Hey, if I'm in grams, I can use the mole concept in the periodic table to convert to moles. So we need the density here. So this is a great example of using density, which will pop up here and there in stoichiometry. So what we're going to do next is we're going to get rid of the liter. For every 1 liter from the density equation, or the density value they gave me, it's 148 grams per milliliter. And you can guess our liters cancel. We're left with grams. And the last step, which I'll leave in red, why not, is I'm going to convert those grams of oxygen. Now, anytime I do this type of stoichiometry, and I didn't do a nice job, I should always tell you what we're starting with, because there's going to be times where we switch from one chemical to the other using those ratios that we had before. So this is oxygen. I should always tell you what value of what chemical, because we're going to be working and changing chemicals using those ratios from a balanced reaction. So in any case, we want to get rid of grams here. And so 1 mole is how many grams of oxygen? Well, the atomic mass of oxygen is 15.99. You can round to 16. There is 2 particles or 2 moles of oxygen atoms in a mole of oxygen. So 2 times 16 is 32. And you can round for me. Some people would want you to use the to the certain number of decimal places on the periodic table, but we're using the atomic mass. This, of course, is a conversion factor from the mole what? From the mole diagram. Or hey, it's just a converting factor that uses the mole concept. In any case, let's get our value here. So I got 178.2 dividing by 1,000. I have to be in liters here to use my density, which is in liters. And then I'm going to times that by 1.48 and then divide that by 32. And I get 0.00824. I'm going to keep 4 sig figs since they started us with 4. So 0.00824, and that would be 2. I'm just rounding off. And this is, again, what do we have here? Okay, this is moles of O2. As I said in class, if you're cool, you don't write the E under the under for mole. So this is our answer here. Notice I'm giving a unit, okay, with what chemical I have in this answer here. All right, so that's my answer, and I want to make this nice and pretty, so let's go with something nice like this. So this would be my answer here. And I'm keeping 4 sig figs because we started with 4. All right, and so that is our answer right there. And I can see that's kind of small if I was using a key for people to read, so let's make that bigger. Hey, okay, a little nicer. Okay, so in any case, moving on. They want the mass in grams of H2 that decomposed. Whoa, remember, there was a solution of H2O2, right? There's a solution. So a solution is a mixture, all right? So we want to find what part of that solution actually decomposed, all right? So notice they want some information about H2O2 here. All right. So this is a great example of stoichiometry where we're going to start with information about the oxygen. And we're going to work our way back toward H2O2. How do I do that? Well, I do that because I know it's a 1-to-2 ratio. So honestly, there are some new skills here, but if you just understand that we're using the ratio of the amount of these particles in the balance equation, it's easy because we have the moles of O2, don't we? So all I've got to do is times it by 2 to get the moles of H2 that was needed to make that oxygen. Remember, we answered the question of how many moles of O2 would be produced given the fact that they said that the solution completely decomposes. The H2O2 completely decomposes. So all of that chemical in that solution, meaning water is going to be left over, breaks apart into water. So we're going to work backwards. So this is how much oxygen we produce if all of that decomposes. So can't we calculate backwards? We sure can. Okay. If you know how many cookies you want to make, can't you figure out how much flour you need to make them? Sure, that's what's happening here. So I know that we can times it by 2 and then convert to grams, but I'm going to make this pretty. So I'm going to start with the moles that I have. Okay, I'll make this bigger. So I got 0.00842 moles of oxygen. I'm going to start always with the number, the unit, and what chemical I'm starting with. Really important. And now, this is the part where I'm going to convert. Okay, or this is the part where I'm using the mole ratios. I can do this. If you look above, it's a 2-to-1. there's 1 O2 to 2 H2O2s. So I'm going to get rid of 1 O2. And the reason why I'm putting O2 is I'm trying to cancel out the oxygen to get my H2O2. And this is the part that makes it stoichiometry. Stoichiometry just means you're using ratios. And it's a how many ratio, so it's mole involved. That's why we need mole concept. And there are 2 here. And again, I'm getting that from the balanced chemical formula. So what I'm doing here is I'm getting rid of oxygens, and now I have moles of H2O2. Of course, it's times by 2. You could have saw that without doing this dimensional analysis. But I'm just going to make it pretty. And now I'm going to times this, okay, by its molecular mass, because I want to convert to, well, I want to convert it to grams, so I have to use the molecular mass. So let's go to a different color. And we know it's H2O2. And so how do we find out the molecular mass? Remember, finding the grams per mole of an atom is called gram atomic mass. Finding the grams per mole of a salt that has a formula, right? It has an empirical formula. It's not a molecule, all right? It's called the empirical mass, okay, or formula mass. And then because I'm using a molecule here, nonmetals, we call this molecular mass. So this solving grams per 1 mole is all about, it's got a bunch of synonyms here, but bottom line is I have 2 hydrogens per particle. So if I have a mole of this, well, then I have a mole, 2 moles of hydrogens. That's what this is. And every mole of hydrogen is 1 gram from the periodic table. So if I look up hydrogen's atomic mass, the mass of 1 mole is 1.00 something, and I'm rounding to 1. So I have 2, hold on, let me just do this nice. So I have 2 H's, just to remind myself. And again, you guys can do this faster. But so that's 2 times the atomic mass of hydrogen, and that's 2. I know my 1 times table is pretty good. Then I have 2 oxygens per particle. So if I've got a mole of this particle, I've got 2 moles of oxygen atoms. So 2 times the atomic mass of oxygen, which is 15.999 something, round to 16, and you get 32. And then what you do here is you get 34 grams per mole. That's the unit. That's the molecular mass, mass per 1 mole. And I'm going to use that value right here. Okay, so I got 34. My short-term memory is gone. So I've got, no, I'll get rid of mole, so mole goes on the bottom. And I got 34 grams right here. Okay, now you didn't have to put it together this way. You could have clearly just times your moles of oxygen by 2 and then converted to grams. But I'm going to show you the nice, clean way of using your units. So in any case, take my 0.00842. How about I turn my calculator on? Okay. All right. Times 0.008242. Times that by 2. Okay. Divide by 1 if you needed to. Times by 34. And I get, I'm going to maintain 4 sig figs. And I'll do it in black. Yeah. So 0.560 and 4. Just rounding to 4. And what did I find? I found grams of H2O2. That's exactly how much reacted. And let's make a nice little box. And why was it stoichiometry, party people? What made it stoichiometry was that we times our starting value by a ratio. And that was the ratios from the balanced chemical equation. All right, good times. Number 4, it's a lot of fun. So calculate the mass of water that was produced. All right, so if we go back to our overall reaction, how much water was produced? Right, so how much water was produced? Well, we know it's a 2 to 1 to 2 ratio. So I don't care how you do this. There's so many different ways to do it. If you notice, if you have your moles of O2, you could times that by 2, and now you have your moles of water. Or if you already have your moles of H2O2, it's going to be the same moles of water. because it's 2-to-2 ratio, and then convert to grams. So what I'm just going to do is just start from the oxygen, since I already have that. So I'm going to start from the oxygen again. Again, many ways to skin a cat. I go navel up, but there's certainly other ways. So 0.008242 moles of O2, and I'm going to use my ratios. I know that I want to get rid of oxygen and I want water. And what are the balanced ratios, the mole ratios? Hey, there's two water molecules to one oxygen. So it's a 2-to-1. We've seen this before. So this expression gives me moles of water, but we want mass. Mass is grams. So I'm going to get rid of mole here. So 1 mole is equal to how many grams? And if we went to the molecular mass party, you would know that 18 grams equals 1 mole. You would do this again, but you would do it for H2O2. 2 hydrogens, 1 apiece, 1 oxygen is 16, it'd be 18 grams. Okay, so I don't think I need to do that. So let's go find that. And again, what makes this stoichiometry is we're using our ratios here. It's not what I wanted. I wanted this. Yes, now I'm being consistent. Okay, so let's go find this answer. So 0.008242 times it by 2. Okay, divide by 1, and then times by 18. And you get 0.2967. And what's this unit? We're finding, grams of what? What's left standing? Water. And of course, I need to make a nice little box here for the answer. Part of my issues, okay? All right, there. And so there we go. Again, we're just using the ratios in the equations. All right. And now you notice we're always converting to moles, right? And I didn't cancel my moles here because we have to be in a how many number to use a how many ratio. We can't take the grams and times it by that ratio, right? Chemical formulas and balanced chemical reactions are not about mass, okay? They're about how many of each. Okay, very, very important. Okay, why am I erasing that? Beyond me. Okay, so any case, last one, number 5. Calculate the percent of H2O by mass in the original sample. Okay, so they want to know the percent of the H2O2. Remember we said that we had H2O2 that was aqueous. Okay, aqueous. What's that mean? Well, it means that you had H2O2 dissolved in water. Okay. So it was a solution. So what's the percent of the H2 in that solution? Now we know that anytime you do a percent, okay, it's a part over total times 100, my friends. And what we know is the total is going to be 6.951. We're finding the percent by mass. So that's the gram total of the solution of the aqueous sample that was in that beaker. And how many grams of H2O2 did we find? Well, in number 3, we found 0.5604. So 0.5604 grams goes there, and I'll change the color. 0.5, well, my short-term memory is gone at this height. 0.5604. 0.5604 grams. Times that by, let's stay color coordinated here, times that by 100. And let's go find that percentage. We're doing a mass percent. This is the hydrogen peroxide. Oh, I should stay in same colors. Making a key too. All right, so this is the H2O2. Exactly. And of course, we'll go black here. And this is the solution's mass. What does the solution have? It has the solvent, in this case, the water, plus the thing it dissolved, which is the H2O2. Any case, so 0.5604 divided by the total, 6.951, times that by 100, and I get 8.06% by mass of H2O2. All right, and you buy 3% or 6% at the store, so this is an 8% solution. So, and you see a 8 hydrogen peroxide solution, let's say CVS or any of the drugstores, that percentage is a percent by mass, done the same way we did here. And of course, I'm going to give you 3 sig figs. I know we have 4 here, but in a percentage, there really is no unit because the grams cancel. So, some people argue that there is, but so 8% be fine. 8.06 I think is fine. And any case, that's my answer there. So again, the only thing different in these questions here is at some point we're using the ratios. Okay, what made this stoichiometry, my friends, are these ratios, these mole ratios, MOL ratios that we get from the balance reactions. Okay, that's what we're doing here. And we're getting that, and from those mole ratios, we're getting our answers. So I hope that helped, and see you next time.